what's the simplest way to describe BCI? Like, what does it stand for? Like, how would you frame it to just like a layperson?
BCI stands for brain-computer interface. And so I think of it as like a modem for the brain. A modem lets, computer plug into a telephone network or fiber network or something. A brain-computer interface lets a computer plug into a brain and vice versa. It takes information from the brain and makes it accessible to the computer, and it takes information from a computer and makes it accessible to the brain.
Maybe walk a little bit through kind of BCI history, or maybe more, you could go really far back, I guess, with like just the discovery that there were like electrical charges in the brains and EEG in like the early 1900s, but maybe just even, that, or also just kind of the quote unquote Utah array. If I understand, that was, I think, early 2000s, I believe, where it was like the first real kind of proof that there you could actually essentially have the brain be instructed via an outside device.
Yeah, I think that the Utah array, there have been, over the last 60 years, a lot of kind of one-off examples of neurosurgeons putting in electrodes into different areas and seeing brain responses in response to different stimuli, or stimulating the brain and getting people to perceive something or move their body. But I agree with you that the Utah array, which is basically a bed of 100 silicon microneedles.
Was it related to like a university in Utah?
It was developed at the University of Utah, yeah.
Okay.
And it was actually, the hardware was developed in 1989.
Oh, wow.
Which is really interesting. It wasn't used in humans until the mid-2000s. It's basically a silicon needle, like the same material that a chip is made of. And it's 100 microns at the base, which is 1/10 of a millimeter. And then it gets really small down to, let's say, like 10 microns at the tip. And then so it looks a little bit like a bed of nails, and it sits on top of the surface of the brain, and then it reaches down about 1.5 millimeters into the brain tissue and records from individual neurons. And so the first applications of this allowed people to control robotic hands, control a cursor on the screen. Now there's recently been a really exciting breakthrough at UC Davis, where there is a patient who lost the ability to speak and tries to speak, and the brain implant is able to tell what he's trying to say and turn it into text at 30 to 60 words per minute.
What was the researchers' impetus in terms of that? Was it a stab in the dark? Did they actually have very high conviction? They knew the right area of the brain, for example, to put that initial array of...
We've known for a long time that there are sensory areas that encode information like visual and auditory, and there are motor areas that essentially tell the body what to do. And so from recording and stimulation experiments in animals and humans, everyone knew that putting a device into motor cortex would allow you to read out intended motor movement. And I think the initial recordings were done in an area that controls the hand called hand knob, and focused on robotic arm control, imagined movement of a computer cursor, later on imagined handwriting. There are what are called intracortical BCIs. That's like Paradromics and Neuralink, and this older 1989 technology, which is called the Utah array. Those devices reach down to the brain and record single neurons. Then there are surface electrodes, like Precision is a good example, or it just came out that Andreessen Horowitz is backing famous neurosurgeon Eddie Chang, who has another surface recording approach. Surface recording is sort of recording the like roar of the crowd when a lot of neurons are doing
and surface meaning on the skull?
Surface of the brain. So It's called electrocorticography, but that's a lot to say, so I just said surface. But recording on the brain surface and then sensing Like when a lot of neurons are doing something very correlated, what can we see?
But not actual electrodes into the brain, but
yeah, electrodes on the brain. So I'll start with kind of those two types. Okay. The best way to think about that in a sort of physical analogy is that intracortical devices, you can think of them as microphones that you're dropping into a stadium. If you drop one microphone into a stadium, you're going to hear the voices of whatever people are sitting on the bleachers around that microphone. If you take the same microphone and you put it in the parking lot outside of the stadium, you will still be able to hear whenever the crowd gets up and does something all at the same time, and the sound is very correlated, like they're cheering, you'll know it. You'll hear the sort of like volume envelope get louder, but you won't be able to hear individual voices in the stands. On the surface of the brain, if two electrodes are within a millimeter of each other, they're more than 50% correlated. And as they get to be within, let's say, 1/10 of a millimeter of each other, they're more than 90% correlated, which means that putting more electrodes on the surface of the brain is quickly diminishing marginal returns versus putting more electrodes into the brain.
Who are the competitors? Is it just Neuralink that's taking am I saying intracortical?
Yeah, there are 3 companies right now that are building intracortical probes. There's BlackRock Neurotech. That's a company that inherited the IP from another company that commercialized the 1989 technology. They're selling research tools to research groups that are producing incredible clinical trial results, but the systems have these, like, we can get a picture of it, I'm sure, but these like 1990s security camera type devices bolted into the skull, which are like create permanent wounds that have to be kept clean. And it's not really a suitable medical device. And also they have some data rate limitations just due to the fact that they don't have as many channels as a Paradromics or a Neuralink device. So they were kind of the BCI OGs, but probably not going to produce therapeutic medical devices that are used in market in the future. And then that leaves Paradromics and Neuralink, both, I would say, technologically very sophisticated companies, but going about things slightly different ways.
So I think we've got a good, at least I think I now have like a good layperson's understanding of how you're getting data out and the right data quickly out of the brain. So essentially, you're analyzing the analog signals quickly and determining what's needed. Maybe some training is needed to determine that once you've got the use case defined, but then it's happening.
Yeah,
because there's only so many words that come out of the brain. Or
the most important thing is you want to know what neurons are firing at what times. And generally speaking, the approach I think both Paradromics and Neuralink are taking is just then send the raw record of what neurons are active out of the body to be processed offline. Because once you're outside of the body, you have effectively an unlimited energy budget, and you have a much more limited space budget to do computation.